I promised you that eventually we would have 3 buckets of energy, and right now we just have 2. And my apologies to those of you that have already been to this week's tutorial. In a perfect world, you would have had this lecture before going to that tutorial. But the way the schedule worked out this semester, it just didn't happen. We already have a kinetic energy bucket. And remember, energy is the capacity to do damage. When something's going fast, it can crash, it can break things. We also have this gravitational potential energy. And it's called potential because it has the potential to do damage. A boulder at the top of the cliff, if you're walking at the bottom of the cliff, should scare you. If someone were to tip it off the cliff, it could turn that potential energy into kinetic energy, which could then crash into you and do damage. Now, let's talk about a new bucket. A bucket that has to do with the energy in a spring. If we think of energy as the capacity to do damage, is there energy in this little toy? Oh, yeah. Yeah. Okay. Now, I got to tell you, it's great being an old man. I mean, not always great. I mean, in the morning it's not so great, but I can get away with this, you know. I've been doing it for years. And my younger colleague, Shannon, she had to teach 205 one year. And so she did that. She pointed it at the student in the front. And the next thing we knew, the president of the university had received a scathing letter about how the student was threatened. His life was threatened in class. And then it went to the department head, and then I had to write letters. But I've got tenure. I can shoot you all. I won't. But clearly, when you have a spring that's compressed or stretched, there's a capacity to do damage. There's energy stored. Have any of you changed the struts on a car? Any of you? Oh, that's scary. I did it once. I'll never do it again. I was being cheap. From now on, if I need that done, I'm going to pay someone else to risk their life. You know, I did it on a little car, a K car. Why would you fix a K car, you say? Yeah. Anyway, this spring was all compressed, and one of the things you have to do is you got to release it. And the trick is releasing it so that it doesn't go through you. Okay? So this energy is real. Now, how big is it? In order to understand that, we need to understand Hooke's law. Hooke's law is named after Robert Hooke, who was a contemporary of Isaac Newton. And by contemporary, what I really mean is Isaac's pain in the butt. Okay, every single time Isaac came up with something, calculus, Robert was right there. Oh, I invented the calculus last week. I just forgot to write it down. You know, gravity. Oh, I already thought of that. I was telling the guys at lunch. Everything that Isaac came up with, Robert said he came up with first. So finally, to get him to go away, we gave him Hooke's law. This is what it is. If you put a mass on a spring, it stretches. Pretty profound? Okay? And we call that stretch delta S. Now, if I want to stretch that by twice as much, how much mass you figure I better put on there? Twice as much. That's Hooke's law. He got famous for that. I'm never going to be famous, but he got famous for that. Okay, so let's look at this. The bottom of this spring is right at 10 centimeters. If I put half a kilogram on here and let it hang, the bottom of the spring is now at 22. It stretched it by 12 centimeters. If instead I put a whole kilogram on there, twice as much mass, Now it's down, the bottom of the spring is at 34. That's a stretch of 24 centimeters. Twice the stretch for twice the pull. Hooke's law. Okay? Now, the way we write that mathematically is that the force exerted by the spring is proportional to how much you stretch it. Okay? We said it opposite here. We said the amount you stretch the spring is proportional to how hard you pull on it. But it dances both ways, forwards and backwards. Now, that's the force exerted by the spring. That's what we call the spring constant. More about that in a second. And that's just how far the end of the spring is displaced from equilibrium. The length that spring wants to be. The length the spring was when it came out of the box from the factory. How much you change that length. Now, this spring constant, first of all, let's talk about that minus sign. That minus sign just tells me that if I pull the spring down, the force by the spring is up. Again, that's not very profound. But that minus sign can get in our way. We already have way too many minus signs in this class, and this one's just never, ever important. So we're typically going to just ignore that minus sign and just use the magnitudes. Now, if I want to know what that K value is, set that delta S equal to 1 in your mind. 1 unit of length. In the units that we use, 1 unit would be 1 meter. That tells you that K is the force that you would have to pull on a spring in order to stretch it or compress it 1 meter. Now, folks, if you stretch this spring by 1 meter, you bought it. Okay, because it's never going back into this shape here. You're going to stretch it all to heck. Okay, so that definition is going to work with the great big springs that they have on the roller coasters at Disney World. You can stretch them by 1 meter or compress them by 1 meter. For this one, what I would do is I would measure how hard I have to pull to stretch it 1 centimeter. And then I'd multiply that force by 100. By 100. Okay? Now, this K value, we call it the force constant. It tells us how stiff the spring is. The bigger the K, the stiffer the spring. So that means that the spring on a car, a Chevy, is going to have a huge K value. And this little guy here would have a very small K value. Okay? The bigger the K, the scarier the spring. The more energy can be stored in that spring. Okay? Now the units of your K value, your spring constant, are newtons. Pronounce this for each meter. Or the newtons required to stretch the spring 1 meter. 1 meter. Let's see if you understand this by solving this problem. You have a bungee cord that's 50 meters long. And then we just, for whatever reason, decide to hang Professor Steve Iger on it. Turns out Steve's mass is 80 kilograms. He's a little sensitive about that. Please don't spread that around campus. What's the spring constant for this bungee cord? The bungee cord acts like a spring. And so solve this problem and tell me what your answer is. Okay, if you haven't got your attendance points, get lucky. Okay. The answer is indeed E, but not by an overwhelming majority. Let's do it together. We have this bungee cord hanging down from the ceiling. It's 50 meters long. And if we hang Professor Iger from it, what we find is that it's 80 meters long. What we care about is this stretch, how much it changed from its normal length. We call that delta S, and it would be 30 meters. Well, by Hooke's law, and I'm going to leave out the minus sign, I'm looking for K. The delta S is 30 meters, so if I knew how hard the spring was pulling on the professor, I'd be done. Well, that requires a free body diagram. The Earth is pulling down on the professor with a weight force, the mass times 9.8, call it 10, or 800 newtons. The cord is pulling up on the professor. If he's not accelerating, just dangling there, this would also have to be 800 newtons. So if I plug in 800 newtons here and solve for K, I get 27 newtons for each meter. Okay, check that your neighbor got that right, please. Okay, this is our final bucket. The energy, potential energy stored in a spring depends on the spring constant, how stiff that spring is, and it depends on how much you stretch it or compress it squared. So that means you pull a spring twice as far from equilibrium, you have stored 4 times as much energy. Now, you'll notice K is always positive. It's a pull per meter. It's by definition positive. Delta S, because it's squared, that's got to be positive. So my spring energy is always positive. Likewise, my kinetic energy is always positive. Mass is positive. V squared is always positive. The gravitational potential energy will always be positive if you choose the lowest point in your problem to be 0 height. And that way all energies will be positive. It will simplify the problem. Folks, a word. On the first and second exams, I gave you every equation you needed for success. I'm not here to see whether you can memorize. I'm here to see whether you can solve problems using the ideas of physics. And that's why I gave you any equation you needed. What I found over the years is that if you don't memorize these formulas, all of them, you don't recognize the players on the field. It's like watching the Super Bowl and not having a clue what the rules of the game are. You're just going to enjoy the commercials. That's all you're going to enjoy. Okay? So, I will not put these equations on the front page of the next exam. If you ask the proctor for one of these equations, he or she will be under oath not to give it to you. Not because we hate you, but because we love you. Because we want you to succeed. And you're going to succeed if you recognize the players on the field. Okay? You got to memorize it by the next exam. You just as well do it now.